Okay, we are going to be looking at sample problem 17.7 to apply the information at the end of chapter 17 here, looking at rotational um, momentum and impulse. Okay, so you'll notice here that we have two gears that are in engagement, and it says gear A has a mass of 10 kilograms and a radius of gyration of 200 millimeters, and gear B has a mass of 3 kilograms and a radius of gyration of 80 millimeters. The system is at rest at this moment when a couple M, okay, so M you'll notice is on B, and that couple and moment mean the same thing. I haven't used that terminology very much, but they they really are the same thing. So if you see couple and moment, they are the same. And you'll notice that couple, capital M moment, has a magnitude of 6 Newton meters, is applied at that gear. Okay. Now, these gears were actually an example, a sample problem we did back in module 3. So the set might look familiar. And actually, back there, when we did this sample problem, the final answer that we had was we wanted to solve what was the force that B put on A. Okay, what was that, the actual force that was generated here between the teeth. Okay, and we got 46.154 newtons. That's actually going to be part of the problem that we're going to be solving today. Now, when we solved it back in module 3, we used the conservation, or I'm sorry, we used work energy to actually get our final answer. Okay. So today we're gonna do, like I said, part of our problem we are going to be solving for that same force, but instead we're going to be using the rotational impulse momentum. Okay, so we're going to find that we do get the same answer. All right, and as you've probably noticed in anything physicsy, right? There's sometimes more than one way to look at it, especially when we're applying the conservation of energy. That kind of is the blanket over everything, right? But depending on the information that you're given, once in a while, these approaches, as we've been looking at them, lend themselves a little bit better. So in this case, there's two ways that we can go about it that'll work to get to the same final answer. But because we're using and we want to apply the rotational impulse momentum. Okay. So anyway, so we'll peek back at that a little bit later to confirm we got the same answer. Now, neglecting friction, determine the time required for the angular velocity of gear B to reach 600 RPMs and that tangential force that B exerts on A. So part B is going to be the one that we're going to compare back to that sample problem 17.2. Okay. So as we do with all of our problems, we're going to start here at the top and we're going to identify what we're given and what we're going to be solving for. So this is sample problem 17.7 on page 1226. Mass of gear A was given to us at 10 kilograms. Sorry. The radius of gyration of gear A was 200 millimeters, but we know that we're going to have to put that into meters. So on that equation sheet that we just generated, for our units, if we look down here, our units for radius of gyration need to be in meters and feet. So since we're in those metric units, we're going to be in meters. Now, you don't have to do a full-blown conversion here. We know that we can move our decimal place 1, 2, 3 places to the left. So it's going to be 0.2 meters. Okay. Our mass of B was given to us as 3 kilograms. And our radius of gyration of B was 80 millimeters, which is going to be 0.08 meters. Again, moving to the left 3 places. And then in the problem, they said that, and I'm putting moment on B because they just called it capital M moment. It's being input on B. So I'm going to keep it as an MB is equal to 6 Newton meters. Now, we do know as we are starting our problem, and I'm going to put it up here by our A's, our WA1, like our before, our starting state, is equal to 0. This is at rest, okay? The radius at A is 0.25 meters. And then our WB1 is also at rest, and the radius there to B is 0.1 meters. Yeah. It was 250 millimeters for A and 100 millimeters at B, but I just put them right to meters right away. What do we need to find, right? What we need to find, and there's two parts to this problem. So part A is we want to know the time for B to reach 600 RPMs. And this is considered WB2. Okay, that's the 600 RPMs. So it's starting out at rest. We're going to apply that moment. And how long does it take us to get up to 600 RPMs for gear B? And then part B is going to be that force. That force B on A. I don't know what to call it. Do I call it something? Hold on. I don't know. I think I just leave it at that. It's totally fine. Okay, so now we're ready to kind of start our problem. Now, as we already know, for this particular problem, and because we're learning about this in this section in 17, our approach is going to be rotational impulse momentum. Okay. We are going to identify our convention here because we do have these rotations as counterclockwise is going to be positive. Okay. Now, we are going to do our diagram, and I'm going to draw. This first circle is going to represent the angular momentum of A1. So we're going to, I should really put this up here. This is gear A. Okay, gear A. And then we'll look at gear B. And so this is the center. I'm just going to show it going counterclockwise. So it's going to be IA, so the moment of inertia at A, times the angular velocity A1. We know that velocity, the angular velocity A1 is 0. So this is going to be 0. Okay, but we'll show that in a little bit. And we multiply it, A times angular velocity A1. Okay. Now, because it's going counterclockwise, okay, we would say that it would be going negative, but it's going to end up being a 0, so it's totally fine. Then we're going to do a plus, and we're going to do another, my circle template here. This is going to be our impulse, okay? So here's the center here, going in a clockwise direction. Our radius is radius at A. And right about here is that point of engagement with gear B. And we would then have the force right here that is going to be generated. Okay. And for this is our impulse diagram. This is going to be times the time. So F times T. Now, this is going to be our plus impulse. And this is going to be 1 to 2. So it's kind of like during, right? And this is our moment times the time. Now we know moment to be force times radius A, and then it's going to be multiplied by the time. So it's going to be force times radius times time. And we'll be filling in these numbers down below in just a second. It's going to be equal to our last circle, and this is our after momentum. So we're going to put our center on here. We know that it's going to go in a clockwise direction. This is going to be moment of inertia of A, angular velocity A2. And this is going to be equal to our HA2, our angular momentum of gear A after or in its second state. This is going to be IAWA2. So if we look, the parts that we have to find are going to be our moment of inertia of gear A. We're going to have that force. It's going to end up being unknown. We know what the radius is, and we also want to find the time. Okay. So we've got to go through and do some calculating here and then plugging them in. So the first thing that makes sense to solve for is going to be our moment of inertia at A. Okay. Now they gave us the mass and the radius of gyration. So we know that in its general sense, mass A times radius of gyration A squared. Now, if you want to go back, we did add this to our equation sheet for the chapter 17 side. And the general is moment of inertia is mass times the radius of gyration squared. So since it's given to us in that form, then that is going to be 10 kilograms here for the mass of A times 0.2 meters. And we have to square that value. So our IA is equal to 0.4. So we'll kind of put our little circle around here. Make sure that your radius of gyration is in meters, not in millimeters. Now, our angular velocity A1 is equal to 0 because we're starting from rest. And our radius A is equal to 0.25 meters. So these two items will take care of the radius here and then the WA1. Okay, now WA2. We know that we need to, this is going to be the velocity, the angular velocity after our gear B is going 600 RPMs, right? Because this is our after effect. So we know that the velocity ratio between A and B can be calculated using the angular velocity of B divided by angular velocity of A. Angular velocity of B is the driver gear, and A is the driven. So if you need to go back to your equation sheet, driver, driven. B is the driver, it's the smaller, faster one, and A is the larger, slower one, okay? But we can also say size-wise, the radius of A divided by the radius of B will hold that same velocity ratio. And we do know both of these, don't we? Okay. So we can say that our velocity ratio is 0.25 meters divided by 0.1 meters, right? So our velocity ratio is 2.5, okay? 2.5. And this is the velocity ratio A to B, which is the two gears that we're dealing with. Now, if we know what the velocity ratio is, and we know how fast B is going, we know it's 600 RPMs, right? Then we should be able to solve for our WA. So we can say that WA, or our angular velocity A, I should put 2 here. I'm so sorry. 2 2's, because the ones are zeros, is going to be equal to our angular velocity B2 divided by our velocity ratio. So we know that to be 600 RPMs divided by 2.5. Okay. Doing that math, we get WA2 equal to 240 revolutions per minute. Okay. I can't use revolutions per minute up in this equation. I've got to convert it to our friend radians per second, right? So go ahead and convert to radians per second. Oh, 3, 2. You should get WA2 is equal to 25.132 radians per second. Do you guys get that? Awesome. Thank you. Now, as we look up here, we know our moments of inertia. We know our moment, it was given to us. Okay. We know the time. Okay. And we know our WA2. So now what we can do is we can go to the next page here and input those values. Okay. So I'm just going to rewrite. Now I'm going to go back to my original diagram. If you remember, these are pluses and minuses. Okay. And the pluses and minuses come from the direction that we're rotating. So if we look here, and the reason we have clockwise, and I didn't tell you this, and now I will, but it'll make sense. So clockwise is the direction of A, because if we look at B, you'll notice the direction of that moment, that red moment there, it is counterclockwise. So because they're engaged, then A is going to be going in the opposite direction. So it is going clockwise. So that's the reason for the clockwise direction on each one of these. That means that these would all be assigned negatives. Okay. So if we go here, we're going to say negative IAWA1 minus, again, because of the because of the clockwise, this is going to be our F times R, that's our moment, times our T. And I'm going to put RA because it's the radius of gear A. Those will be together. Equal to minus, again, clockwise rotation, IAWA2. Sorry. Be consistent. All right. So let's put our numbers in. We know that this is equal to 0, so this is going to be 0 down here. Okay. Then what we're going to do is we're going to pull out the F times T here. Okay. So this is going to be minus F times T because we don't know those two values, but we do know that it's a radius of 0.25 meters, radius A. It's going to be equal to a negative moment of inertia A, we calculated earlier to be 0.4. So that's going to be 0.4 times WA2 is the 25.132. I'm not going to put the radians per second because we know it's in the right units. There we go. So you'll notice that our impulse is going to kind of stick out and it's going to stay there by itself. So if we go ahead and we multiply out, this is going to be F times T times 0.25 meters. And then this is negative, this is negative. They both become positive. We're going to have 0.4 times 25.132. But then we're going to divide both sides by 0.25 meters. And our F times T, our impulse, is going to be 40.2 Newton seconds. We're just going to put our little cloud around that because it's not a final answer, but we will use it in a little bit. All right, now that was gear A. This impulse is going to also apply on gear B. Okay, so it'll come in handy for us. So now we're going to look at gear B. Okay. So starting with our before angular momentum, and then our impulse, and then our after angular momentum. Okay, so this is gear B. Let's equal. Now, in this case, we're going to be rotating counterclockwise. All right. And this is the angular momentum. So this is going to be I, B, W, B, 1. Okay. And we can put that down here. This is counterclockwise. We can put it positive, but we know that IB times W, B1, B1 is starting from rest. So that's going to be 0. Plus, this is going to be our impulse. Now, when we look at gear B engages with A right about there. Okay. Now, gear B is rotating. That moment B is going to be going as pictured in the illustration in a counterclockwise direction. As it does that, gear A is pushing back on it. Okay. So that means that if you recall, we had our force going down and to the left. This was the driven gear, okay? The driver, the force is going to be perpendicular, but it's going to go in the opposite direction of rotation because it's like it has to push A out of the way. So it's feeling A pushing back on it. So this is going to be F times T. And then the radius is going to be B. Okay. So we know that this is our impulse, and this is going to be equal to we're going to take into consideration our moment at B times the time. That's the impulse rotationally. But then we also have this force times time times the radius. Okay, and that's the radius at B. Now, the reason that this is going negative is because if we put our finger at the center and we pull in the direction of that force, it is going to go in a clockwise direction. So this one's clockwise, this one's counterclockwise, counterclockwise. Does that make sense to everybody? Okay, this MB is going counterclockwise, so it's positive, but the F times T will be clockwise, so it'll be negative. It's going to be equal to the angular momentum of the after. So it is going to continue to rotate in a counterclockwise direction, and this is going to be IB WB2. WB2. So this is going to be a positive IB WB2. All right, then we just got to fill in all of our values. So we need to calculate the moment of inertia at B. So IB is going to be equal to the mass B times the radius of gyration B squared. So if we go back to the beginning of our problem, mass B was 3 kilograms and the radius of gyration is 0.08 meters. Then we have to square that. So I get 0.0192. Okay. Then the next thing that's, I don't know, kind of easy if you would to calculate, let's do our WB2. Okay, WB2. We know WB2 to be equal to 600 revolutions per minute. We can't use revolutions per minute. We have to convert it to radians per second. So 1 revolution, 2 pi radians, 1 minute, 60 seconds. Minutes and revolutions cancel out. We have radians per second. So our WB2 is going to be 62.83 radians per second. So that'll be here. So we've got those guys. All right, and then we're ready. Our F times T that we have up here, that's going to go in this place. We know our radius of B, I think that was 100 millimeters or 0.1 meters. We know our moment. So our only unknown here is going to be T. This is going to be good. So let's see what we got. So our IB is times 0 is going to be 0. Plus our moment at B is 6 Newton meters times the time. Okay, so I'm doing this line right here. Then we're going to have a minus the F times T. Okay, F times T is the 40.2 Newton seconds. So 40.2 times the radius. So that's 0.1. I'm just going to put meters so we know that that's the radius. It's going to be equal to 0.0192 times our WB2, 62.83. I'm just going to put the radians per second so you know that that's what that is. Again, you don't have to put the units in, but it's just kind of like little markers so we can see it. Okay, so go ahead and you should be able to solve for T because T is our only unknown here, which is going to be our answer for part A. So you should get your time equal to 0.871 seconds.
Got it.
Perfect. Thank you, Danny. All right, so that's part A. How long does it take us to get to that 600 RPMs or 62.83 radians per second? It takes 0.871 seconds. Okay. Now, part B was what is that force that's being generated? Okay. So the force here is F times T. Now, if we know that the time is 0.841 seconds, I'm sorry, 0.871 seconds, we can say that F times T, okay, we know that to be equal to 40.2 Newton seconds. Okay. And now we know the T is equal to 0.871 seconds. Okay. So then we can say F is equal to 40.2 Newton seconds divided by 0.871 seconds, right? Because our time divides on both sides. So our F is equal to 46.15 newtons. Now, as I had told you earlier, when we did similar problem, and part of it was to calculate that very same force back on sample 17 too, using the work energy theorem, we also got 46.154 newtons, and we got 46.15 newtons here. Okay, so same answer, two different approaches. Okay. So any questions on that particular problem? All right. So what I'm going to do is that takes care of the sample problems or the practice problems that we have for Module 5. So if we take a peek back to our practice problems, when you hand in the practice problems, you'll be handing in the equation sheet with both sides. So it'll be the Chapter 13 Module 5 stuff and the Chapter 17 Module 5 stuff. So you'll hand that in. And then additionally, you've got 4 Chapter 13 sample problems or practice problems. And then we've got this one 17-7. Okay. So make sure that you get those in as part of your practice problems. I'm going to stop our recording here, but we will do an overview of the application problems in the next short video that we do.